Okay, so welcome to part 2 of the graphical models class. So today we're going to look at dependence. No, not the one that in the coffee cup. I hope you all had a good cup of it this morning. So it's not going to be mathematically very complicated today, but there'll be a few conceptual things to pay attention to. Because if you recall from Monday, we basically went through this very simple case of 3 random variables, right? Brain, brawn, and university graduation. And we saw that even within that very simple case of 3 random variables that have a very specific simple connection to each other, it's still possible to actually get something that's fairly complicated. And what we're going to do today is we're going to abstract from this very special case a set of more general rules that we can then apply to general directed graphical models. So on Monday already there was some question about, when are things dependent on each other, when are they not dependent on each other, stuff like that. And we're actually going to work our way through very, very simple cases of essentially always 3 variables each. And then we're going to put that together to give us a general framework and actually an algorithm for inferring whether something is dependent on each other or not. Okay. So the simplest thing that we can do is we can look at a chain of random variables. So you have A, B, and C, and B depends on A, and C depends on B. Think of that as one short part of maybe a Rube Goldberg machine where you first, toss an egg over, and in the end it makes you breakfast with maybe a coffee. And here, of course, you have one step following the other in a Rube Goldberg machine. This is exactly the situation that we have here, where A causes B, B causes C. Now, in that case, I can actually just ask, well, what would happen? Well, first of all, I can write out the joint probability distribution. So P of A, B, and C is, very unsurprisingly, P of A times P of B given A times P of C given B. Right? Are there any questions about that so far? Because this is really basic stuff, and if you're stuck here, it could get a little bit difficult later on to follow. Any questions so far? Okay. So now, if I condition on B, well, conditioning on B just means simply you go and write out P of A, B, and C and divide by the corresponding quantity where you summed over the A's and C's. Well, keeping B fixed, of course. Right? Because we need to make sure that that new probability distribution is normalized again. Okay, so seeing a couple of surprised faces here. I need to sum. So if I have, well, more generally, P, well, let's pick a different color, P of X and Y, then from that it follows that P of X given Y is P of X and Y divided by, what do I have to do? P of Y. Base rule. And the same thing is what happens here, just that, well, mentally substitute for Y the variables A and C. Sorry, this is X, of course. And substitute for B, Y. Now, how do we get P of B? Well, we have to sum over A and C. So that's what's happening in the denominator here. And the one redeeming quantity that you actually get is, and this looks like complete coincidence, but it actually isn't, is that the sum in the denominator can actually be expressed reasonably cleanly, namely by summing over A's and summing over the C's, while, of course, the B is fixed. So rather than summing over the quadratic number of different choices of A and C, I sum in one bracket, so this is this one here over the A's, and the other one over the C's. Got it? Okay. And the other thing that I've done is I've actually gone and factored out terms that depend only on A and B and terms that depend only on C and B. So now I have basically that P of A and C given B is a function that's a product of something that depends only on A and B and something that depends only on C and B. In other words, it factorizes in A and C. So conditioned on B, A and C are independent of each other. And in graphical model speak, what I've simply done is observing B. So what people typically do is they shade that variable. So in other words, this variable here is written in solid. So when you see people writing out graphical models, the observed variables are usually shaded. If they're not shaded, sometimes they put them into double circles or make them a little bit more solid than the other ones. So when you open a paper and they draw models of that form, everything that's in solid black or shaded or some otherwise, that's usually observed variables. Everything that's not shaded is the stuff that you don't know and that you actually want to infer. Okay. And what we've just learned is, by this very simple mathematical manipulation, is that if I have a chain and I condition on any of the variables within the chain, then the children of that variable and the parents parents and all that way up, they become conditionally independent of each other. Okay. Yes?
So here you use the factorization to prove that?
Correct.
Didn't you already assume that by noting that P of C given B and A is P of C given B?
Well, yeah, that's basically what the quote proof is, right? So proof is maybe a grand word for showing what I just did. So what I've done is I just showed that under the assumption that my probability distribution can be written in this form of taking this directed graph and turning it into algebra, that in this case, if I observe B, A and C are independent of each other. What we will, however, see is that in some other cases, this isn't quite so trivial. So let's take the converse. So let's assume that A and C are actually caused by B, right? So all I've done is I've taken the same chain of three variables and I'm just, changing one of the arcs. So rather than the arc from A causes B, I had now B causes A. So again, I can write P of A, B, and C as P of A given B, P of B times P of C given B. And now, if I observe B, actually things are independent of each other. And if I don't observe B, then A and C are dependent on each other. So that follows simply by integrating out B. So I have this, bit of a hairball here, right? Right, so I basically have the sum over B, and now B couples A and C. Okay. So there is no obvious way how I can easily separate this. There might be some very specific assumptions on A and, A given B and C given B and P of B that might possibly make this independent, but that's extremely rare. So one thing would be, for instance, that B can only have one possible value. In that case, trivially it factorizes again, but in general it does not. Or for instance, one thing would be that A given B doesn't really depend on B. In that case, it also factorizes. Now, if we, however, condition on B, then things do become independent of each other, because now all we have to do is just look at a normalized distribution in A and C. Yep.
Could you give an example, please?
Okay. So let's assume that whenever I drink coffee, I am first of all awake, and secondly, I'm in a good mood. Right? Now, from that you can infer that, even if you don't see me drinking coffee, you'll find a very strong correlation between me being happy and me having drunk coffee. So me being awake and me being happy, right? So you can infer, well, Alex being happy and Alex being awake are maybe in some way dependent on each other. However, if you actually watch me in the morning at breakfast and see whether I have had a cup of coffee, then my happiness level and my alertness level will become independent of each other, conditioned on having observed this. Or, for instance, suppose I have, a bunch of lights here, right? And I have a single switch that switches all those lights on and off. If you don't see the switch, you will see that the variables of lights being on are going to be strongly dependent on each other. If you do observe the switch, well, that's no longer the case because it's now just a function of whether you had a burned out light bulb, right? So that's an example of where a common cause all of a sudden makes things conditionally independent of each other if we observe. Yes?
So the P over there, is that like a posteriori probability?
No, P of B is just my assumption of what I assume that B is distributed as. So we're not talking statistical inference yet. So statistical inference is basically something, well, okay, in a way, P of A and C given B would be a posterior probability over A and C given B. But we're going to do this now in a much more general form than what we did before for regression or classification, where we observed some data and then we looked at some posterior distribution. Here we have a whole bunch of variables, we condition on some of them, we want to reason about how the rest of them behaves, conditioned on the things that we observe. So, for instance, if you have a medical treatment, you might condition on which drugs you've given the patient and, maybe whether you applied surgery to him or, other things. Maybe some things that you also observe, maybe, whether he's, alert and breathing. And you then want to infer things like, what's his life expectancy, what's his level of pain, and, maybe which diseases he has, conditioned on those observations. But these are now much, much more complex, more sophisticated graphs. And I want us to go through the basic ideas in it with graphs of size 3, because they pretty much, in a nutshell, capture all the things that we could be observing. Right? So what we had before is a single chain of 3 random variables with all directions going the same way. Now we have one case where we have a common cause. And in the case of a common cause, conditioning makes things independent. If I don't condition, basically if I don't observe B, then things are dependent on each other. The other way around is if you have a common effect. So let's say, for instance, A is the light switch, and C is whether the voltage is available. Then, and B is whether the light bulb is on. Right? And now, this is a common effect because I need to have the light switch on and the light bulb, and the electricity needs to be there for the light bulb to actually go on. And so now, conditioned on the light bulb being on and off, switch and electricity actually become independent of each other. Okay, sorry, they become dependent on each other, sorry. Yeah, would be kind of stupid otherwise. Because initially you can assume that, whatever I set the light switch and whether the electricity is there, these are just independent, events, independent random variables. But if I observe whether the light is on, I can make inference about both things at the same time. So conditioning makes things dependent. And again, it's the same algebra as what we had before. I'm writing out P of A and C given B. I need to normalize over A and C. And what you can already see is that, namely in the numerator, that's the relevant part here, things do not factorize. Because what you have is exactly this factor here, P of B given A and C, that couples A and C in whichever way you want it to be. Okay. So in one case, we saw that conditioning on that random variable creates conditional independence. Here, conditioning on that random variable creates dependence. So you need to be very careful which way these arcs go. But the good thing is you really only have those three different cases. And with them, you can pretty much go and analyze all of your fancy graphical models. Yes? So case number 2.
So if we had a structure of the problem where C is a cause for A or A is a cause for C, for example, and we have an arrow between, like either from C to A or from A to C, would the probability computations be the same if we remove that arrow?
So if I had an arrow that went from A to C in addition to this, right? Let's do that. So from that, you can already see that even if I don't, okay, so first of all, if I don't observe B, I will have A and C being actually dependent on each other. That was already the case before. Now, if I condition on B, then A still influences C, right? So, for instance, assume that B is whether you actually do surgery. A is whether the surgery is effective, and A is whether you actually have the disease, and C is whether you're cured. So in that case, well, basically, independent of, regardless of whether you observe whether the surgery happened or not, if you don't have the disease, you won't be cured of it by the surgery, right? So adding this arc doesn't actually make things independent. It'll actually just increase the dependence. Let's formalize that because there's this. So there's this notion of deseparation. And deseparation is what, in directed graphical models, can be used to analyze whether things are dependent on each other. And don't worry, we'll go through this in detail, but it's basically those three rules that we had so far. So assume that I have a directed acyclic graph, so a DAG, and I want to determine whether sets A and B of random variables. So this doesn't have to be necessarily just a single variable, but it can be a larger set, whether they are conditionally independent of each other given C. And the questions about, well, graph connectivity and so on are quite pertinent here, except that it's a little bit more complicated. So there is a simple reachability algorithm. It's called the baseball algorithm, like Reverend Base, with which you can execute this on the graph. And if you have reachability, then they are dependent on each other. And if you don't have reachability, then they are independent of each other.
Question.
Yes?
Two questions. First is how do you define the independence between two sets of variables?
Oh, okay. Okay. So the question is, how does independence between sets of variables is defined? Well, that's actually fairly straightforward. So remember we had basically P of maybe XA and, given XC times P of xb given xc. And in this case, we clearly had, actually, let me drop the subscript and just call them this way. P of A given C, P of B given C. And in this case, you would write that A conditionally independent of B given C, right? Now, if I have a set of variables, I could have this being A1, A2, A3, and maybe this being B1 and B2.
Do you mean between all pairs of A and B?
Well, it's between the entire set. So you can have situations where each variable independently might very well look independent, but where as a joint they are not. So here's a simple example. Suppose I take two variables and then compute their parity. So basically C is A XOR B. And there, C is going to be independent of A, and B is going to be independent of C, because, well, the parity just flips the sign. But as soon as I observe both of them, I can immediately determine the parity. So the parity is usually the most evil example by which you can break a lot of things. It's a good way of working that out.
Yeah, still, what is this relationship between the sets?
Well, the set is basically just that now my random variable isn't just, a single bit, but maybe 10 bits, right? So this is now my new random variable. And if I have maybe text and pictures, then my new random variable is the struct of sets and pictures. So think of when you define data types in programming languages, right? You can basically make a data type composite of smaller objects, and my new random variable is now the entire new data type, right? So that may help, if get your head around that concatenation operation.
So that joint distribution are independent.
So in this case, the joint distributions are independent. So it's basically one data type and another data type conditionally independent of a third data type. Right. Question?
So when you say can be reached, you mean by following arcs?
Correct.
In the direction in which they're pointing?
Correct. Well, that is exactly what's on the next slide. So here are the transition rules. And you can't just go and implement that. As a matter of fact, I think there are a bunch of implementations of that algorithm out there. And this slide is courtesy of Sam Roweis. There are more complicated ways of how to explain this, but this is probably about the simplest that you can have. And here's basically what happens. So when we have a chain, then, so basically here we have four groups. One is where you have three variables where the variable in the middle has been observed. The second one is where it hasn't been observed. The third one where you only have a single child or a single parent, and that's not observed in the last case when that child or that parent is observed.
It's a little bit confusing.
So, well, basically we have graphs of size 2 or 3, right? These are the graphs of size 3, the chains. These are chains of length 2. Now, in those, I have basically, well, I can direct the arcs in either way. And so I now need to look through the various cases how I can direct the arcs, right? So in chains of length 3, where the middle variable has been observed, because that's what we're asking for, does this couple the rest? We can have either the arcs going all in one direction, or all outgoing, or all incoming. Obviously, if all the arcs pointed to the left here, that would be equivalent to this case, because all I have to do is just flip. Same direction of arcs. Here, it's just that we don't observe the thing in the middle. Now, if we have 2, then it can either be a child or a parent. Right? And we can either not observe that child or we can observe it. Okay, so those are the cases that we actually need to go through. And all I'm doing now is I'm just mapping what we did on the previous 3-4 slides into those rules. And that's about the only picture you need to remember. Yes?
The arrows that are not connecting nodes, the ones with the lines in front of them or not with the lines in front of them, or that curve backwards, what do those mean?
So that's what I was going to explain now. I was just going to explain first what the logic of this diagram is. So if you bear with me for a minute, a lot of things will become clear. Let me explain the slide. Okay, so remember what we had is we have basically, as the first case, the chain of 3 random variables where we had this simple causal connection, right? And in this case, well, if x causes y and y causes z, then x and z and x are dependent on each other. So that's what it means that these arrows here go in both directions. So x can reach z and z can reach x if y isn't observed. However, whenever we observe y, remember this was case 1, then x cannot reach z and z cannot reach x because things are conditionally independent of each other here. Okay? So that explains the first 2 transition rules. Now, the next rule is what happens if we have a common cause. If we have a common cause and the common cause is not observed, so this is Alex drinking coffee, then Alex's happiness and Alex's alertness become dependent on each other. That was exactly what we had here. So again, if you have arcs going out in both directions, then you can transition through that vertex. If you have arcs coming out in both directions and you observe it, then you cannot transition. So this symbol here means that transition is blocked. Furthermore, we had the situation where we have a common effect, where if we observe the common effect, namely the light being on, then all of a sudden the light switch position and whether that building has electricity become dependent on each other. There was this thing here. And here, if they are not observed, if the common effect is not observed, then x and z remain independent of each other. These are really the basic transition rules. What follows here is just corollaries of that. We'll get to that in a moment, but what we really covered here are just the 3 cases that we did just before with algebra. And I went through that in a very, very basic way because otherwise these diagrams can look surprising. So there's nothing on those diagrams yet that we haven't seen in just the past 10 minutes. So do those first 6 figures make sense to you guys? Okay, good. Now let's move on. So the next thing is, what happens if I have a single child, and that single child, well, basically is not observed? Right? Well, in that case, nothing particularly happens here, because that single child that's not observed, things just stop. So this is basically x going from x to y. And if y is not observed, well, that's it. Now, the only thing that happens is, when that child is observed, it tells me something about x itself. So essentially, what I get is that if I do graph traversal, I need to respect the direction of the traversal that I'm following through. And it basically just means that traversal comes back up. That's the only thing that happens here. So that's the same thing as what happens there. Basically, it comes back up. Okay. Next, if I have a unobserved cause, then again the traversal backs up. If I have an observed cause, it doesn't back up. Because I can treat this essentially just as an independent random variable in its own right. And I would have had to originate from there at some point for reachability anyway. Yes?
Are these 4 cases on the right, with 2 known cases, just special cases of left, what x?
Exactly. So effectively that's what it is, yes. So if you look at it, well, that's basically x causing y. Sorry, x being caused by y. And if I observe y, then this blocks up. So that's this case and this one here, right? So now what happens if I have vertices with more than 2 edges? What I do is I can basically make that same argument for every single triplet of edges. And that's it. The only reason why I basically had to go through the case of 2 edges because you have to essentially define what happens if the inference backs up, and you can basically see that it's the same thing as if x and z or here are merged respectively. So basically, merge x and z here in all of those 4 cases, and you get exactly these 4. Yes?
For the one in the bottom left, let's say X and Z are 2 switches that turn on the light.
Okay. So the question is, what if X and Z are both switches that can supply electricity? And Y is whether the light is on. So let's say you control one switch, I control another one, and we independently decide whether we switch it. So our switch positions are clearly independent of each other. Now, if I observe that the light is on, then I can infer from that at least one of the switches has to be on. Right? So in other words, if I observe the light, then I can figure out, and if I didn't switch that switch on, I can immediately infer from that you must have switched it on. So now all of a sudden I can do inference from what I am doing up to you by just looking at the light switch. I don't have to see what you're doing with the switch. Right? So it helps sometimes to go through those simple cases, with switches that are probabilistic switches, right? So basically where if I switch things on, the light doesn't always come on or stuff like that. Because otherwise, so this doesn't only work for deterministic, this works for logic as well, but it also works for things where you don't have quite probability 1, transitions. But it helps to debug it with that. Okay. So now that we have those transition rules, and as I said, those 4 rules are just special cases of these, we're done, and we can essentially apply this to a graph. So now let's actually ask the question, are x1, x2 and x3 independent of, basically x1 and x6? So I'm observing x1 and x6, and I want to know whether I can now independently infer x2 and x3. Okay, so good. Okay, good, fine. So we basically do the baseball algorithm. Okay. So first we go and have the arc, coming out and going to x4. Well, nothing really happens there because, it's just an unobserved child of x2. So that's where things end. Remember, that's one of the rules from before. Now, we still have 2 more arcs that we can send out, right? We could send out arcs in this direction here. We could send out one here. Okay. So let's see what happens if we go to x1. x1 is a common cause of x2 and x3 actually. And since I'm observing it, again, nothing happens, so this is also terminated. Okay, which leaves us with one last choice, namely going through x6. Now x6 is a common observed child of x2 and x5, so this goes through. x5 is caused by x3, so this goes through. And oops, we've now seen that there is one dependence arc going from x2 to x3. So in other words, x2 and x3 are not conditionally independent of each other given x1 and x6. By just squinting at that graph, I think it would be ridiculously hard to just look at it and infer that x2 and x3 are not conditionally independent. Right? But by actually executing this algorithm, you can see it immediately. Yes?
Observe x5 alongside x1, x6, then x2 and x3 will be.
Yes. So the first thing is, yes. So we could check what happens. So if you were to observe x5, sure, that's the end. Because now you have basically an incoming arc into something that's observed, and so now, that would block it, right?
Can you go to the previous slide?
Also, for instance, observing, well, yeah, that's okay. So also, not observing x6 will actually make things independent of each other. So this is seriously counterintuitive, right? So this is exactly the, explaining away or causing dependence by observing something. So if I just observed x1, things would be fine. Because then the transition would get blocked here. Okay. Any other questions?
Yeah, just what if x5 is observed?
Well, if x5 is observed, well, we just had that, we just talked about that like a minute ago. Then,
I forgot.
Because
this is not either transition rules.
Well, no. If x5 is observed, well, that's yes, it is in the transition rules. Let's go back to them. So this is exactly this rule here. If x5 is observed, then I cannot transition through it.
But they are the two consecutive blocks.
Okay, that doesn't matter here. Okay, but what matters is basically whether you can transition through one of those vertices. So those transition rules apply to, can you transition through Y?
Okay.
Right. And
So the color of x and z doesn't matter.
no, doesn't matter.
Okay, that makes sense.
Okay, good. So this is a very simple graph reachability algorithm, and you can actually just implement that. So this is sometimes called baseball. And there are different ways how to do it reasonably efficiently, but you basically want to color the vertices that you've already traversed in certain ways, or the edges rather. Yes? If we observe x2 and x3, then, well, asking whether they're independent of each other doesn't make a lot of sense anymore, right? Because then I already know what their values are. What you could do is you could ask, well, if I observe x2 and x3, are x1 and x6 independent of each other? Or are x1 and the other group being x5 and x6, or maybe x6 and x4 independent of each other, right? And so what I would suggest that you do, because it just requires a bit of practice, you take that graph and you actually just practice those transitions, right? I mean, it's very, very simple. Either you practice them or you write a little piece of code, and it's probably going to be one screen of Python, and you're fine. By the way, graph traversal is something that people like to ask a lot in job interviews, also for internships at a lot of internet companies. Right? So, hint, if you ever do one of those interviews, make sure you have your sorting, merging, graph traversal algorithms up to date. This might be a good place to practice it. Yeah. Fun occurs when you try explaining things in Python and the interviewer doesn't know that Python doesn't have pointers. I had that once happen to me. Okay, good. So summing things up, what I've talked about is, well, how to deal with dependent and independent variables, how in some cases observing something can make stuff dependent or independent, and you really just need to go through the cases of how stuff depends on each other. And then the baseball algorithm, and I think this is probably pretty much the simplest explanation that I know of for how to motivate it and how to actually work through it. That will actually give you this fairly effectively. So you should be able to do this for any given graph, right? And you may have to do that in the homework, and it's a good thing to know it also later on in your life. So those things are popular exam questions, just because it's very easy to draw a new graph, right? Yeah. So now let's move on to structures, because, well, it's kind of awkward to always draw, very specific, explicit graphical models between, small numbers of variables. That's extremely tiring to express. So just in the same way how you design a chip or how you design, a large building, you basically design blocks, building blocks, and then you repeat them. You basically use them as macros, and you compose larger objects by composing those macros. So what we're going to do now is we're going to introduce macros. And the first thing to do is basically to introduce for loops. So we already saw a very simple graphical model a long time ago, namely when we did naive Bayes, right? Where we basically had the assumption that whether something is ham or spam determines whether a particular word occurs or not. So theta was ham or spam, and the xi's were basically whether a certain random variable occur, the chances of that one occurring. Okay. And this was supremely awkward, because what we had is basically that, it takes a long time to even draw all of those xi's. So a really easy way is to say, well, just repeat them, because they all have exactly the same, structure. So what you can simply do is you can simply say, well, the xi's depend on theta, and I have many of them. And usually you would have a small index variable here saying I equals 1 to 10, for instance. So this is really just like a for loop. Now the nice thing is you can nest that, right? So just like you have a nested for loop, I could have now some variable alpha. And now this influences theta j, and now you have xij, and you have the j's out here. That's a nested for loop. And with that, I've immediately created a tree of dependencies. And that's actually not an uncommon model. For instance, if you want to, well, let's say you want to model survival in a hospital. And you have many hospitals, and you have many patients in each hospital. So then, the x's, for instance, would be the patients in hospital J, and these would be the survival rates in hospital J that depend on some prior alpha. So this lets me infer both what the general survival rate in hospitals is. It would let me then adjust those survival rates for each hospital separately, because maybe UPMC is really good and some other hospital is rather not so great. And then here you have the individual patient surviving or dying, right? So this is a very simple hierarchical model that I can do with, very, very simple terms. This is actually something that's being used, well, not just for hospitals, but for instance for computational advertising. In computational advertising, you want to find out whether an ad will get clicked on. And what happens is that basically, different advertisers, have different skill levels of designing catchy ads. And so you basically would have as your outer plate, for instance, all the advertisers. And then as your inner plate, you would have the specific ad that's being run. Because maybe the Ford Motor Company is much more skillful at designing ads than maybe Toyota, right? So then you would have, the outer plate being, Ford versus Toyota, the inner plate being the specific ad that's being run, right? So that's a very simple case. Now, here's another one that's a little bit more complex. Let's say we have supervised learning. So in supervised learning, we have maybe some parameter like the weight vector. In this case, I'm just calling it theta. And that governs how I'm generating my covariates. So for instance, if I want to tell apples from oranges apart, theta governs my distribution of images. And then W governs, whether I call it an apple or an orange. And so what I have is now a simple subblock of a graphical model of this dependence inside between x and y, which depends on outer variables W and theta. But then I basically have that repeated many, many times over because I observe many pairs of x and y's. So that's another macro block. And this is basically all we've been doing for the past few weeks in, this very, very simple graphical model. And you can immediately see that, in order to infer W, well, you may not necessarily need to know theta terribly well if we observe the x's. Right? So now you can basically do exactly that reachability argument. We have a cause, you observe the outcome of that, so you don't really need to go back. So this is exactly if I have, a chain of A, B, and C, and if I observe B, then C and A become independent of each other. So that tells me exactly that I don't really have to do much about theta in order to infer this. That's essentially why supervised learning works. And here's the math that goes with it, right? It's basically P of theta, P of W, then P of xi given theta, P of yi given xi and W. Yes?
How does this change when you have a prior on W you're using?
Okay. Okay, good. Great question. Well, so now we have a prior on W, gamma. Okay, done. So what you would now do is you would have to change P of W into P of W given gamma, this guy here, and that then, times P of gamma. Or if gamma is observed, then you don't really need to model it anymore otherwise. So now sometimes I don't quite know what gamma should be, so then I can maybe have a hyper prior, and I get this, and you get a longer chain. And then maybe you set eta. So when people talk about hyperpriors, that just means you walk one further step out in your prior. In graphical model speak, it's nothing particularly fancy. People have been doing this forever, but if you invent a new term, you usually get a couple of papers in for that term. Okay, well, joking aside, it actually was an important insight that this also applies to supervised learning, and the algorithms got a lot better, but it basically just means that something that seems like a big insight is sometimes rather trivial once you get your notation right. Okay, but that's in many cases, right? Okay, any questions about that so far? So we already had this, right? So basically, we only care about the yellow part. Now, let's look at Markov chains. So, we can basically ask whether, let's assume life is a Markov chain. Well, okay. In other words, yesterday's state determines today's state, which will determine tomorrow's state, and so on. Which is the case, provided that yesterday's state is really everything that there is to be known about the world of yesterday. That means all the books, all the information, everything. And in which case, this is a perfectly reasonable assumption. So yesterday's state shouldn't be only what happened yesterday, but also whatever else is known. Right? So, well, it gets kind of awkward to write it this way, so let's write it as a plate. And so now all I have is just, an arrow ingoing, an arrow outgoing. And there's a little bit of slack in the graphical definition because, well, it's not really clear from that, where the incoming and the outgoing arrow would go, but the convention is that this just loops back on itself. Okay. So now we can actually apply this Markov chain whenever we don't necessarily observe something. So this is a hidden Markov chain or hidden Markov model. So HMMs or hidden Markov models are nothing particularly scary at all. So it's, for instance, the unobserved part is the user's mindset, and the observed part is the user's action. So, for instance, maybe I'm currently in my mind dreaming about some wonderful grant proposal, and what's coming out of my mouth is a description of the hidden Markov chain, right? Well, that would make for a horrible lecture, but yeah, and I wouldn't dream of grant proposals. No, thank you. Question?
Well, why do we have fast as feature?
Sorry, why do we have what?
Fast over there on the left-hand side of the list.
On the plate? Well, okay, so why do we have an ingoing arc and an outgoing arc? Well, because, today's state depends on yesterday's, and it affects tomorrow's. So that's why I need both edges. Otherwise, it's not understandable what my model means. Yes?
How do you know if the chain is meant by that, or if it's meant to branch off? Like you have your incoming thing branching off.
Yeah, so that's exactly where the notation is ever so slightly sloppy. So what usually happens is that you can use the plate notation to quickly convey the idea of a model. And when you engineer something, that's usually the language that you will use. Once you then go and actually have to implement it, you will actually go and write out the conditional probability distributions anyway. So most papers in graphical models go as follows. They first have like a textual description of the problem they're trying to solve, then they have a graphical model as in plate notation drawn, and then there is a section which is called inference, and there they explicitly write out the probability distributions, and that's where they do the math. And then you have another section called experiments, and they show that the stuff actually works. And if you're unlucky, your referee skips over the math and just looks at the pretty pictures. But it's also that it's just ridiculously much easier to remember this picture of a plate than to actually remember the equations. So it's an extremely useful kludge. People have tried making this into a formal description language, and there are some issues sometimes with it. So Winbugs, for instance, tries to do that, where you can actually drag and drop graphical models and then run it. The one that works a little bit better is Stan, as in MC-Stan. And that is probably one of the more scalable latent variable inference packages out there right now. Okay. Yes? Pardon? Not necessarily. So in that particular Markov chain, I just try to explain. I try to motivate it by past, present, and future. But for instance, if I'm Rip Van Winkle and I lived in the forest, then I would not have observed the present, but would have observed the state of the world 20 years ago. Okay. Or for instance, in a hidden Markov chain, it may be that what you're observing is the audio of a text being read, and what you want to infer is the text. So speech recognition is exactly one of those cases where you try to infer the latent state from the observed state. For instance, you're doing that right now, because so effectively what happens is there is some idea forming in my mind. It comes out as voice. This is transmitted through the room. It goes into your ears, and you are going to try, I hope at least, make sense of what I am saying right now. So insofar, you're basically trying to infer my mental state from the sound waves. You're doing exactly the HMM inference problem right now, except that I hope you're using more than just the 1 second past context state. At least you should, otherwise it's kind of awkward. Besides speech recognition, you can also use it, for instance, to model how a user traverses search results. Because if you, let's say, search for some very specific server and you don't find the results, you will keep on reformulating the query and add query terms, remove terms until you maybe find a site that sells this thing. So this is now an entire query chain. And what your search engine should be capable of doing is infer from that chain that this is really that specific server, that specific thing that you wanted, rather than anything else.
Question on this example.
Yes?
So wouldn't you really have the like arcs coming from the blue circle to the white circle as well? Seems like the action actually influences like next step.
Okay, so what you would have there, okay, good question, is actually a slightly more complicated model, because what you would have is, this is maybe the user's mindset, that's the observed user's action, which then again influences maybe what, let's say, Google returns to you, which then influences maybe again the user's mindset at the next step. So what you'd get is, okay, let's just look at the simple plate notation here, is something like so, which then affects the next guy. And so there you already see how this simple plate notation can run into a little bit of trouble. What you would do in this case is actually write a plate that includes the latent state and the latent state at the next time, and you just, in addition to that, add your edges. Right? So that's a simple example. Now, here's the formal description of what's going on. In Markov chain, I just have, p of x given theta, then xi plus 1 given xi. And in the hidden Markov chain, I have the same thing, but then I observe the y's given the x's. And I have that basically as a separate term branching off. So there's nothing in this expression that should be new, given the directed graphical models that we've already been doing. And you can already see that there's this slight inaccuracy in how we write this out, because you basically need to specify what happens at the beginning of the chain and also at the end. Right? Whereas this is how you discuss the models with your colleagues. This is how you implement them. Okay. Here's another case. Factor graphs. So you maybe have a couple of latent factors and you have some observed effects, and you want to know whether, what causes them. So again, maybe I have some latent interests, and then what I observe is, what news I watch, which emails I send. And the user profile is, maybe some social connectivity, some events, any of those things. So can I actually turn this into, graphical model? Yes, I can. So, for instance, I can assume that the x's are just, given by, just some latent causes of the y's, and then the y's are all independent of each other. Yep, people have used that quite a bit, and that's actually PCA. So remember, we did PCA last week, and we assumed that this was a nice way of getting a Gaussian graphical, getting a normal distribution, and we find some latent causes. So now what we basically have, that the latent causes are exactly those variables y. they're individually normally distributed. And then what I'm observing is basically a rotated version of that and possibly with some noise added. So sometimes this model is actually called Bayesian PCA. And yeah, if I don't have a simple Gaussian assumption, then this will give me independent component analysis, and I could do that too. Quick question, the graphical model that goes with that is actually very simple. What we have is here is one set, and here is another set. And you just have one edge. That's it. Yes?
Is X the top or the bottom?
So in this case, the x's would be here, and the y's would be up there. Because the y's are all independent of each other, and the x's depend on all the y's. So actually what you would also have in addition to this, you would also have maybe some vectors v that govern this. So the v's are basically exactly those rotations. And then if sigma were a random variable in its own right, then maybe you would have a inverse gamma hyperprior, prior on the sigmas, and you can change things together. So in other words, as soon as you start modeling real problems, you need to actually make sure that all your variables are, properly determined in some reasonable way, or that they have a prior that is reasonable in its own right. Yes? What's the meaning of VI? Well, the VIs are basically, for instance, the eigenfaces in PCA. They're what? Sorry, I cannot understand what this. I cannot parse the word. Did somebody else manage to parse? Oh, in the general case, well, there may be some mixing matrix. So, for instance, let me give you an example: the cocktail party problem. So, the cocktail party problem, and I encourage that you do the following thing now: take one finger, stick it in your ear, just in one ear, and try to still listen to what I'm doing. Yes, try it. Make sure you can only hear from one ear. You can take the finger out now. But what you probably would have noticed is that it gets ridiculously much harder to understand what I'm saying as soon as you block one ear. If you were unlucky enough, you probably at some point took an airplane with a really bad cold, and when the plane landed, that exactly happened to you. And it's horrible because you can't really figure out what's going on when you're hearing with one ear. Because what your brain is doing, it is basically solving the cocktail party problem of demixing all the cacophony of sounds such that you can separate, for instance, what I'm trying to say from the rest of the background. And the mixing matrices, so basically the mixing components of how various sources arrive at various receivers, this is exactly what this matrix V would be, for instance. So in the cocktail party problem, what we simply have is we have all the sources. We then observe a number of mixtures, and we are not told what the mixing coefficients are. And the goal is to then go and separate the independent sources out from each other again. So that's ICA. Okay. And your head is actually pretty good at doing that, despite the fact that you only have 2 ears. If you had 3 ears, it would get even better. So people are using that. So if you have a more recent wireless space station, you would probably see something like MIMO advertised on it. And it would have like a number of different antennas. That's effectively what it's doing. It's basically using several signals that are arriving with a slight delay, and then demixing things in such a way as to receive exactly the data from your poor cell phone or laptop. And yeah, that wasn't possible maybe about 15 years ago because processors weren't fast enough to do that. And that's also why you can pack a lot more data into, spectrum by having wireless base stations for, cell phone carriers also use MIMO. Okay. I think I'm slowly but surely getting kicked out soon. Let's just look at one or two more examples, namely recommender systems. And what I want to get to in this case is here now I have for loops that are interleaved. This is a complete no-no if I write code where I have for loops that don't always coincide, right? And the challenge there is actually then to implement this in a computationally efficient way, and you can write a lot of papers about that. I mean, most of the good papers about that have been written, but so I basically have users and have movies, and both have some attributes, and the combination of those attributes then leads to a rating. But I don't really see that for all the users, and we'll get to the recommender systems in a lot more detail in a separate class later on. So the challenges are actually, multifold. And it's basically, how do we go and design those models? So there's some common engineering sense. There's computational tractability that you have to worry. And you need to basically need to make sure that you can actually efficiently solve the problems. So we haven't actually talked about sampling, dynamic programming, message passing, any of the standard algorithms for doing inference in those models yet. We'll get to that over the next few lectures. But I wanted to make sure that at least you have some idea of the basic language, how you express those models. We haven't actually looked at how you do a lot of operations with them. But if you don't understand the language, then looking at the algorithms to do operations in them is kind of a little bit more difficult. So I strongly recommend that you go through these structures and try to maybe just play around and express some of the real world problems that you have, or maybe some of your research in terms of such models. If nothing else, this might actually lead to some interesting insights, and then maybe you can write a nice paper about some of those things. Okay. So next Monday, we'll do dynamic programming. Okay. Okay, so that's that. Okay, good. So thank you for coming, and then see you next Monday.